Hi students, I am Dr. Neeraj Upadhyay, an assistant professor in Department of Chemistry, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar, and coordinator of this course again with you for presenting next lecture or our MOOC. Today we are going to learn about basics of photochemistry, including laws of photochemistry and some of the photochemical processes. Absorption of a photon of light by a molecule or chemical leads to the change in its electronic structure. Subsequently, its energy state is also altered, and this photon absorbing molecule may react with other molecules in a different way. The energy in form of photons absorbed by the molecule can itself cause photochemical changes or changes in the neighboring molecule is called photochemical energy. As you know, light is an electromagnetic vibration dispersed in quantas, while photon is the minimum amount of energy which carries the energy. In other words, photochemistry is the study of reactions which occur in the excited state of the molecule, or it is the study of the interaction of electromagnetic radiation, that is visible, ultraviolet or infrared radiation, with the matter, leading to the physical changes or into the chemical reactions. The sun is a major source of radiation energy on the earth. A few of numerous processes comprising photochemical reaction involving organisms are photosynthesis and vision. You can see the science of vision on your screen. Photographic processes are the best example of the use of visible light to produce chemical changes on the photographic plate and being employed well over a century. On the screen, you are seeing the electromagnetic spectrum and the energy ranges for the particular spectral region. An organized study of photochemical reaction began by end of the 19th century and early of the 20th century. The photochemical reaction were first studied by Giacomo Siamixian, an Italian chemist, and Paul Stilber, the German chemist, at the end of 19th century, while they used sealed flasks exposed to sunlight. For photochemical reactions, mostly UV or visible energy, the wavelength of this is in between 200 to 800 nanometer are used. Photochemistry is indeed the fundamental mechanism for all the photobiology. During the process of photochemical reactions, an electromagnetic radiation provides the energy required for the activation or development. Absorption of photons should individually carry an equal amount of energy required for activation energy of the order of 100 kJ per mole and bond energies of the order of 200 to 400 kJ per mole. Functions associated with light. For a representative photochemical reaction, the function of light is as follows. A, on attack of a photon with energy h nu, convert into B, and in this process delta G is the amount of free energy involved. Here we have two different cases. Case A, if light act as a reactant, then it lead to the synthesis of product B, or it can inhibit the reaction by photostabilization of reactant A. Case 2, if light acts as an energy vector, it leads to the non-spontaneous or endergonic formation of product B and in the energy storage. Now, let us discuss about the second type of reaction. Now, let us discuss the photochemical reactions. If delta G is smaller than 0, such type of reactions are called spontaneous reaction. In these reactions, light acts as a catalyst, thereby enabling molecule to overcome the activation barrier or by lowering the activation barrier. These reactions are known as photocatalytic reactions. For example, H2 and Cl2 combine to form 2HCl. A second type of photochemical reactions are there in which delta G is greater than 0. Such type of reactions are called non-spontaneous reaction. Here, the energy required for the reaction is carried by the light. The partial light energy is transformed into chemical energy. The example of such processes are natural photosynthesis. On the screen, you can see the energy profile diagram for a normal reaction and catalyzed reaction. Let's compare the photochemical reaction versus thermal reactions. In the photochemical reactions, in case of photochemical reactions, the process is only done through absorption of light, while in case of thermochemical reaction, the process starts with requirement of it or with evaluation of it. In case of photochemical reaction, the process takes place in presence of light only, while in case of thermochemical reaction, there is no involvement of light required. In case of photochemical reaction, they are independent of temperature, but in case of thermochemical reaction, the reaction very much depends on the temperature because it affects the rate of reaction. The rate of reaction in case of photochemical reaction is dependent on the intensity of absorbed light, while in case of thermochemical reaction, rate of reaction is not affected by intensity of light. Instead, it depends on the temperature. In case of photochemical process, the free energy change is negative or positive. It does not matter, reaction may proceed by a different path. While in case of thermochemical reaction, the free energy change should be or must be negative, only then the process is feasible or spontaneous. Now, let us talk about the importance of photochemistry. The photochemistry has wide prominence to all the research areas of the chemistry for scientific and societal development. Some of the major areas are organic synthesis, synthesis of strained multiple bonds, synthesis of cyclobutanes, oxytanes and 1,2-diols, synthesis of polycyclic compounds, synthesis of reactive intermediates, that is nitrines, carbenes, radical, etc. In analytical chemistry, the application of photochemistry involves in fluorescence spectroscopy and luminescence studies, in imaging techniques, in the study of chemical sensors. In case of material sciences, the photochemical applications are in photopolymerization of materials, identification of studies of photochromatic materials, and in photography of clean energy through the photochemistry without carbon dioxide emission. You can see the reaction water by using a photocatalyst can break into hydrogen and oxygen. The reaction is very much important in energy generation, and you will see in future some process like this where you can get your petrol or you can get energy freely and no need of petrol is required. In case of photobiology, it is used in photochemistry of nucleic acid, amino acids, proteins, lipids, etc. It is also used in the photosynthesis, in the visual transduction and photocarcinogenesis. In case of photomedicine, the process is used in photochemotherapy and photodynamic therapy. Now, let us talk about laws of photochemistry. The first law is the Gunther-Draper law. It is the first law of photochemistry which states that only the light absorbed in molecule can produce photochemical change in the molecule, or light must be absorbed by chemical substance in order to photochemical reaction to occur, or light must be absorbed for photochemistry to take place. R is when irradiated by a light with energy h nu get excited and convert into R star, which finally convert into the product. The radiation absorbed in this process can be written as IA is equal to I naught minus I. This concept is simple and is the basis of appropriately perform the photochemical and photobiology experiments. No photochemistry will take place and photobiological effects will be observed if light of a specific wavelength is not absorbed by a chemical substance, even if the substance is irradiated with that particular wavelength of light or so long time. If photon or light energy is absorbed by molecule and it results chemical change, the quantum efficiency or quantum yield is defined as number of molecules reacting in a given time divided by number of quanta of light absorbed at the same time. The efficiency you can assume like how much quanta or how much photon are producing the reaction, or you can say the fraction of the photons absorbed that is actually promoting or proceeding a chemical reaction. The second law is Stark-Einstein law. This rule is also recognized as the law of photoequivalence. According to this law, for each photon of light absorbed by a chemical system, only one molecule is activated for a photochemical reaction. Or if a species absorbs radiation, then one particle is excited for each quantum of radiation absorbed. This law describes for each photon of light absorbed by a chemical substance, only one molecule of it will be triggered to cause a photochemical reaction. However, this law is correct if the intensity of light is ordinary. If high powered lasers are used, two photon reaction can also take place. For instance, after absorbing two photons, the molecule is activated and reaches to a higher energy state than the energy state produced by single photon absorption. For a chemical processes, delta G, that is the free energy change of the molecule, can be calculated as N into h nu or Na into Hc by lambda, where Na is the Avogadro number and nu is the frequency of the absorbed radiation. But if you convert the process into the molar form, because in chemistry we generally see the reaction in the form of mole because it is handy. So, in that case a new definition is made. 1 mole of photons are written as 1 Einstein, and this is equal to 6.023 into 10 to the power 23 photons. Therefore, the quantum efficiency can now be calculated as rate of chemical reaction divided by quanta absorbed per second. Means quantum efficiency is rate of chemical reaction divided by the rate of photons absorbed. Now, let us talk about the Einstein equivalency principle. According to the principle, only one photon from a light ray can be absorbed by one particle of chemical substances. So, in this case delta E is equal to h nu, and h nu is absorbed by a particle or atom or a molecule of reactant R naught, which get excited into R star. The same process when you convert into molar form, then for 1 mole of chemical substance you need 1 mole of photons, that is you need 1 Einstein. Here delta E is equal to n h nu, where n is the Avogadro number. One molecule absorbs only one photon, or 1 mole of substance absorbs 1 mole of quanta, thus it can absorb 1 Einstein. Now, let us talk about the Bunsen-Russell law of reciprocity. It states that a photochemical effect is directly proportional to the total amount of energy regardless of the time needed to deliver the quantity. It is factual. If the chemicals are in a test tube, however, the cellular response to radiation generally involves an order of interacting biological reactions, thereby making highly improbable quantity for x time the linear relationship. Now, let us talk about the Beer-Lambert's law. It is a combination of two laws, the Beer's law and the Lambert's law. The law defines the quantity of light either absorbed or transmitted by the colored substances. The weakening of transmitted light is related to the properties of substance the light is travelling through. The Beer law states that the concentration of the colored particle in the solution is directly proportional to the intensity of the color of the particle, while the Lambert's law states that the quantity of the light absorbed by a colored solution depends on the length of the cuvette or the depth of the liquid through which the light is travelled. Before one understands the details about Beer-Lambert's law, following terms are needed to be understood. Absorbance. Absorbance is the quantity of light absorbed by a sample. Concentration. Concentration is the relative quantity of a solute confined within a solution or in a certain volume of space. It is a quantity of solute per unit volume of the solution. Incident light, the light which falls directly on the sample. Scattered light, it is the light emerged but in a different direction from the incident light. Transmitted light, the light which emerges and continues in the same direction of incident light. Molar absorptivity or molar absorption coefficient, it is a measure of absorption strength of a chemical species at a particular wavelength. Monochromatic light, the light possessing only single wavelength. Path length, the overall length of the path travelled by the light ray. So, these were the terms I think you should be needed before learning the Beer-Lambert's law. Now, consider a ray of light falls on a material, then it can be absorbed, scattered or transmitted. This you can see on the picture on the screen. When each wavelength of light passes through the spectrometer, firstly the intensity of light crossed via reference cell is measured and it is generally referred as I naught. That is, I naught is the intensity of absorbed radiation. Further, the intensity of light which passes through the sample cell is also measured for the wavelength and it is referred as I. So, if transmitted light I is less than the incident light I naught, it means that sample has absorbed some amount of the light and this amount of light is basically represented by I naught minus I. Therefore, a computation or calculation is done to measure the absorbed light by the sample, which is expressed as absorbance A. The A of a transition depends on two external conversions. First, the absorbance A is directly proportional to the concentration of the sample in the solution used in the experiment, and the absorbance is directly proportional to the path length through which the light is passing through. Means the absorption of light depends either by the absorbing molecules. So, higher the number of absorbing molecules, higher will be the absorbance, and also to the path length, because as the path length will increase, the chances of absorption by the molecule will also increase. So, the absorbance will depend on the concentration of the sample and also onto the path length of the sample. So, according to first assumption, absorbance is directly proportional to the concentration C. Absorbance is also defined as A equal to log I naught upon I, and this absorbance is basically proportional to the concentration or to the path length. So, our second assumption is expressed as absorbance is directly proportional to path length L. Somewhere L is also represented as B. Combining these two equations, absorbance A is now proportional to C into L. If we use a proportionality constant, then the proportionality can be transformed into equality and therefore, absorbance A will become epsilon into C into L, where epsilon is called molar absorptivity constant. This formula is generally known as the Beer-Lambert's law. However, it can also be described by the equation A is equal to log I naught by I equal to epsilon CL. The limitations of Beer-Lambert's law. The law is not valid when the non-monochromatic radiation are used. Also, it is not valid in case the temperature are changing during the experimental measurements. The law is applicable only to the dilute solution. Also, deviation may occur if the solution may contains impurity or dissociation or association of molecule take place during the process. Now, let us talk about the fluorescence. Emission of photons from electronically excited state is called luminescence, which has two types. Type 1, the relaxation from singlet excited state, this is called fluorescence, and type 2, the relaxation from triplet excited state, this is called phosphorescence. While exposed to the light or other radiation, certain substances absorb the energy and then instantly start re-emitting the energy. Such substances are called fluorescent material, and this phenomenon is known as fluorescence. For example, organic dyes like eucene, fluorescein, etc., and vapors of mercury, sodium and iodine. So, before proceeding, let us talk about principle of fluorescence. The fluorescent phenomena occurs via various energy states, which are as written on the screen. Ground state. It is a stable or most stable stage of a molecule wherein two electrons present per orbital having opposite spin and are paired. Singlet excited state. This state is the state of higher energy wherein electrons in the orbital have the opposite spin orientations. It means the spin of electron does not change during excitation or absorption. Frank Condon principle. The triplet excited state, which is the excited state wherein the valence electron present in different orbitals having same spin orientation by spin flipping. This process of reversal of spin is called inter-system crossing. So, in the figure you can see, if E0 is the energy of ground state, it absorbs energy h nu 1 from the photon and get excited. At the same time, after relaxation, the excited molecule or excited state of the reactant release the energy h nu 2. This is called emitted light of fluorescence or phosphorescence. This you can see on the diagram shown here. So, here some terms are also needed to be to understand. These terms are absorption or excitation. Here also some terms are needed to understand. We are following these terms one by one. Absorption or excitation. Upon absorption of light, a chromophore is excited to some higher vibrational energy level of singlet excited state S1 or S2. The process occurs at a time scale of 10 to the power minus 15 second, which is much faster to that of the molecular vibration or vertical transition. So, during this process, generally nuclei does not change its place. Vibrational relaxation. It is also known as the solvent collisions. The vibrational relaxation is efficient in which electron goes to lowest vibrational level of the same electron state within 10 to the power minus 12 second or less. The excitation of vibration state encompasses adequate energy to break a bond, whereas vibrational relaxation also has sufficient energy to break a bond. Internal conversion. It is a phenomenon wherein the electron crosses boundary of electronic state to lower electronic state, that is from S2 to S1. It is very efficient, therefore, compound do not fluoresce during the internal conversion. If vibrational level of two electronic state overlap, it can cause pre-dissociation or dissociation of the molecule. External conversion. It is also considered as the collisional quenching derivation. Decrease in collision lead to increased fluorescence or phosphorescence. The better the fluorescence can be accomplished by decreasing temperature, increasing viscosity and decreasing concentration of the quenching agent. Overall, you can see or summarize all these terms in the Jablonski diagram. Here you can see when light incident onto the material which is in its ground state of E0 energy, it get excited to higher energy state. In the figure it is S2, and the time taken for this absorption process or this process is 10 to the power minus 15 second. This time is very short, and in this femtosecond time generally nucleus does not move from its place. But during this process our molecule may get excited to upper vibrational level, and the vibrational relaxation in the S2 level is also needed. This type of relaxation is called vibrational relaxation, and generally time is taken in this process is 10 to the power minus 12 second. This time is also very small. So, in this process you can see a internal conversion is there, means after excitation of S2 the molecule can come to the lower energy state by internal conversion process, and in this process energy is not going out in terms of photons, but it transfers energy in terms of heat to the neighboring molecules, and therefore, the molecule may de-excite from S2 to S1 level. After further vibrational relaxation, the molecule is now in a position to fluoresce, and therefore, from S1 to ground state molecule is to come, and the time taken in this process is generally in the range of 10 to the power minus 8 or 10 to the power minus 9 second. Basically, it is in the range of microsecond to nanosecond, and this process is called fluorescence. So, if the de-excitation from S1 to ground state is there, this process is called fluorescence. But we can have another process. The molecule may go into a inter-system crossing process, in which if the molecule is in the excited state S1, it can cross the system transferring some energy to the neighboring molecule, and this energy or this process is called inter-system crossing. The molecule reaches to triplet state because of the spin flipping, and here since two different orbital is having similar spin, so the stability of such two orbitals are greater, and therefore, the molecule stays in this process for a longer duration, and finally, from the lowest energy state of T1, molecule may release energy to the surrounding or in the form of photon, and this energy or this process is called fluorescence. The time taken in this process is sometime very large. It is generally 1 millisecond to 100 seconds. Let us see a spectra on your screen in which the relaxation process or energy released is shown. The relaxation of molecule from the lowest vibrational energy level of the first excited state S1 to vibrational energy level of the ground state S0 by emitting light is known as fluorescence, that occur in the time scale of 10 to the minus 9 second. Relaxation to the ground state takes place faster than the time scale of the molecular vibration, that is vertical transition. Notably, the energy emitted is generally lower than that the incident photon. In general, for a molecule, the wavelength of the fluorescence remains unchanged. It is irrespective of the excitation of wavelength. So, as I told you, in case of fluorescence, the emitted radiation has generally lower energy than that of the absorbed radiation, and therefore, in the fluorescence spectra we can get two type of wavelengths. One is the absorbed wavelength, which is of lower value, and the second is the emitted radiation, which has the higher wavelength value or lower energy value. So, a fluorescence spectra contains two types of process, one is the excitation process and other is the emission process. You can see on the screen the diagram. Just we discussed that the energy of the absorbed radiation is higher compared to the energy of the emitted radiation, means the wavelength of absorbed radiation is lower and wavelength of emitted radiation is higher. So, the absorbed radiation is generally of lower wavelength, and when the emitted light is taken, it is in the red shift or of lower energy. This kind of shift is called Stokes shift. The magnitude of Stokes shift is affected by the internal conversion. The longer the internal conversion will go, the more will be the Stokes shift. Certain substances continuously glow for some time, and even after removal of the external light. Thus, the phosphorescence is actually a slow process of fluorescence or a slow process of glow. For example, zinc sulphide and sulfates of calcium, barium and strontium, they show the phosphorescence process. The phosphorescence process occurs by radiation with less transition followed by the emission. In this process, the intersystem crossing is present. This you can see on your diagram, we have just discussed it about. In the intersystem crossing, the energy of S1 and T1 are nearby, and therefore, during intersystem crossing, singlet state to triplet state is done by spin flipping. Even though triplet state is lower energy than a singlet excited state, it cannot be directly assessed through electronic excitation, since the pathway would vibrate the spin selection rule. Since the pathway will violate spin selection rule. Therefore, it is essential to know how singlet excited state S1 converts into triplet excited state T1 via intersystem crossing. So, let us talk a little about intersystem crossing. It denotes a non-radiative transition between two excited states of different multiplicity. The intersystem crossing takes place via inversion or flipping of spins of the excited electron of singlet excited state, resulting in two unpaired electrons with the same orientation but in different orbitals to obey Pauli's exclusion principle, leading to the triplet state with spin +1 and multiplicity +3. Due to spin multiplicity of 3, this state is called triplet state. However, the transition between two states of different multiplicity are formally forbidden, but vibronic and spin orbit coupling mechanism decrease the pure character of the initial and final state of the system, and therefore, intersystem crossing becomes probable in some cases. Can be seen from Jablonski diagram, the transition from first excited triplet state to the ground state S0 is known as phosphorescence. You can see T1 to S0 transition is also forbidden owing to violation of spin multiplicity rule, but it is sometime allowed when vibronic or spin orbit coupling is there. So, the lifetime of this kind of transition becomes higher in between 1 millisecond to 100 second and is significantly larger compared to fluorescence which goes in between 1 microsecond to 1 nanosecond. So, phosphorescence is for a longer duration. In this module, we learned about details of electromagnetic spectrum and role of light as energy. We also learned the elementary idea about photochemistry and photochemical reactions along with differences of photochemical reactions with thermal reactions. We learned three laws of photochemistry: Grothus-Draper law, Stark-Einstein law and the Bunsen-Russell law. We learned Beer-Lambert's law, its limitations and application in estimating the concentration of samples. We also learned about fluorescence, origin of fluorescence, principle and various energy states through Jablonski diagram and the Stokes shift. Finally, we learned about the phosphorescence, its transition, lifetime and examples. So, this is all about this lecture. Thank you very much for listening me.